Hi, my name is Dustin Scriven. Today I wanted to talk to you about the construction and commissioning of the Texas Neutron Detector Array, or as we call it, TexNeut. Um, the motivation of this project was to design a new high-resolution neutron detector that could be used at Texas A&M as well as other university-based research centers and laboratories with good time of flight energy reconstruction for use in things like basic nuclear science, astrophysics, and even some security applications. Um, the array is composed of 120 of these pseudo-bar detectors. Each bar is made of 6 crystals of the fast neutron gamma discriminant organic scintillator called paraterphenol. And then each stack of crystals is wrapped in a 3M enhanced specular reflective film. The bars are read out as our conventional neutron detector style bars on one readout on each end. And in our case, we use these fast Hamamatsu R1450 photomultiplier tubes. And those signals are read out and recorded by ASICs, which are application-specific integrated circuits, which were provided by Washington University in St. Louis. These ASICs are able to integrate the signals in multiple different ways, which can be determined by the user, as well as record timing information. We did the commissioning experiment of the prototype detector, which was made of 48 position sensitive bars, in early December at the Cyclotron Institute. And we put the array on the back of Texas Active Target, the TexSAT TPC, on the Mars rare isotope beamline, where we could produce some radioactive beams and use TexSAT as a reaction chamber to hold our gas target and use it in thick target inverse kinematics. During the time period that we ran, which was about 2 weeks, we first started with a stable beam of lithium-7 and impinged it on a tantalum foil to produce Coulomb excitations so that we could see this sharp gamma peak in the time of flight spectrum, which would help give us time calibration. And then we evacuated TexSAT, so it just became essentially a scattering chamber, and filled it with, placed a CH2 target, and we did 7 lithium PN. Then we removed that target and filled TexSAT with isobutane and turned on all of the tracking detectors on the inside, the micromegas, the 2 sets of micromegas that we have in there. And we performed the same experiment again, and this way we can make sure that the TPC is working, and that we can validate it with a spectrum that we know what it should look like. So once we confirmed that TexSAT was operating and we saw preliminary spectra coming out of the neutron detector and seeing tracks in TexSAT, we changed the beam to helium-6, where we ran helium-6 PN in TTIK, and then after a few days of running helium-6, we switched to lithium-9, which is a science project that I'm personally involved in, is looking at states in trying to understand states and structure of lithium-10 through this PN reaction, as well as a PP reaction, which we did last year using TexSAT also. The preliminary results were very exciting. On the bottom left, you can see kind of a hit map. So we can use the coincident photomultiplier information to get position information. And the very nice thing about these pseudo-bar detectors is that they are position sensitive. And so we can see a discrete spectrum rather than a continuous one like you might see in a conventional scintillator bar. And so here you can see those hits. There's clusters in the vertical direction, which indicate the hit location of the individual crystals in the bars. And then we time tagged all of our events with a scintillator, a fast plastic scintillator, just upstream of TechSat, where we could see the beam come in, and that was fed into a TDC. The stop of a TDC, and the neutron detector was the start. And this way, we eliminate a lot of background as well. And so just by looking in the first row of bars and only at the PMTs on the top, you can get a really nice spectrum of the 7-lithium PN reaction. And so we can gate on neutrons here. Paraterphenol is a very good neutron gamma discriminator. And when we make a rough gate, we can start to see this 3+ resonance very clearly in the 7-lithium PN spectrum. And then doing a similar thing, going to the helium-6 PN, you can again see a very sharp resonance here, which is a 3½ - excited state in helium-6. So to conclude, the detector array works really well. We only had a problem with a few of the individual bars, but overall, the entire experiment was extremely successful. And we were able to measure neutron spectra and see features that were very expected. So to continue, and in the future, we're going to continue building more bars. This is just a prototype array of the first 48 bars. There's another 70 or so bars that we need to assemble to fill out the array. And then in terms of the analysis, we need to start looking at coincidence information between the top and bottom photomultiplier tubes, which gives us the crystal by crystal position resolution, which will drastically improve our energy resolution, despite these being quite broad resonances. And then also to include in the TechSat portion of the analysis, the track reconstruction, which gives you the vertex location of the reaction, which again improves the energy resolution. And this is useful for the 7-lithium, helium-6, as well as the lithium-9 PN reactions. And then, like I just mentioned, the lithium-9 PN reaction needs to be analyzed, and that'll have its results analyzed in conjunction with some lithium-9 PP data, where we also used TechSat in the thick target inverse kinematics mode to do proton elastic scattering, and we're looking for an isobaric analog state in some highly excited beryllium nuclei there, so that we can infer some properties of lithium-10. So thank you for listening. Enjoy the rest of the SSAP and the rest of the posters. Thanks. Bye.